Quantum Computing, a documentary. Imagine a world where the boundaries of possibility are constantly expanding. A world where the most complex problems we face can be unraveled and solved with unprecedented speed and efficiency. Picture a future where diseases that have plagued humanity for centuries are cured, where climate change can be mitigated through precise modeling and intervention, and where the very fabric of reality is explored and understood at levels we never thought possible. Welcome to the frontier of quantum computing, a revolutionary technology that stands poised to redefine the limits of human achievement. To embark on this profound journey, we must first delve deep into the enigmatic realm of quantum mechanics, the fundamental theory that describes the behavior of energy and matter at the atomic and subatomic levels. In the early 20th century, the scientific community was confronted with observations that could not be explained by classical physics. Phenomena such as blackbody radiation and the photoelectric effect revealed that energy is quantized. It exists in discrete packets known as quanta. This realization challenged the very foundations of physics and led to the development of quantum theory. At the heart of quantum mechanics lie principles that defy our everyday experiences. The first of these is superposition. Unlike classical objects, which exist in a single state at any given time, quantum particles can exist in multiple states simultaneously. Imagine a spinning coin that is both heads and tails at the same time until observed. In the quantum world, this isn't a mere thought experiment. It's a fundamental aspect of reality. The second key principle is entanglement. When particles become entangled, the state of one instantaneously influences the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein famously described it, suggests a level of interconnectedness in the universe that challenges our classical notions of locality and causality. These extraordinary principles form the cornerstone of quantum computing. Traditional computers use bits as the basic unit of information, which can be either a 0 or a 1. Quantum computers, however, use quantum bits or qubits, which due to superposition can represent both 0 and 1 simultaneously. This allows a quantum computer to process a vast number of possibilities at once, exponentially increasing its computational power compared to classical systems. The visionaries behind quantum computing. Let's embark on a journey into the fascinating world of quantum computing by delving into the minds of the visionaries who laid its very foundation. Understanding where we are today requires appreciating the bold ideas and groundbreaking work of pioneers who dared to think beyond the conventional wisdom of their time. In the early 1980s, the realm of physics was abuzz with new discoveries and challenges. Among the leading figures was the renowned physicist Richard Feynman, a man celebrated not just for his profound intellect, but also for his ability to communicate complex ideas with clarity and enthusiasm. Feynman was grappling with a significant challenge that had emerged in the field of computational physics: simulating quantum systems using classical computers. Classical computers, the machines that power our current digital world, process information in bits that are either a 0 or a 1. They follow the well-established laws of classical physics. However, quantum systems, the incredibly tiny particles like electrons and photons, don't adhere to these classical rules. Instead, they operate according to the principles of quantum mechanics, where particles can exist in multiple states simultaneously, a phenomenon known as superposition. Feynman recognized a fundamental mismatch. He realized that simulating quantum systems on classical computers was inherently inefficient. As the complexity of the quantum system increased, the computational resources required grew exponentially. This meant that even modestly sized quantum systems were beyond the reach of classical computational methods. In 1982, during a keynote speech at the first conference on physics and computation at MIT, Feynman proposed a revolutionary idea. What if we built computers that operated on the same quantum principles as the systems we were trying to simulate? He introduced the concept of a quantum computer, a machine that could harness the peculiarities of quantum mechanics to perform calculations far beyond the capabilities of classical computers. Feynman famously stated, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." He suggested that by using quantum bits, or qubits, which can exist in superpositions of states, a quantum computer could efficiently simulate any quantum system. This was a groundbreaking proposition, as it opened up the possibility of exploring complex quantum phenomena that were previously inaccessible. Around the same time, on the other side of the Atlantic, another brilliant mind was independently exploring similar ideas. David Deutsch, a theoretical physicist at the University of Oxford, was deeply interested in the fundamentals of quantum mechanics and computation. In 1985, Deutsch published a seminal paper titled Quantum Theory, the Church-Turing Principle and the Universal Quantum Computer. In this work, Deutsch extended the Church-Turing Principle, a foundational concept in computer science that defines the limits of what can be computed, to the quantum realm. He proposed the notion of a universal quantum computer, a theoretical machine that could perform any computation that a classical computer could, and potentially solve problems that are intractable for classical computers. Deutsch went further by introducing the first quantum algorithm, now known as the Deutsch-Josse algorithm. This algorithm demonstrated that quantum computers could solve certain problems exponentially faster than classical computers. It was a profound insight that provided a concrete example of quantum computational advantage. The ideas put forth by Feynman and Deutsch were revolutionary. They challenged the prevailing understanding of computation and opened up an entirely new field of study. Their work ignited the imagination of scientists and engineers worldwide, leading to the birth of quantum computing as a research discipline. In the years that followed, researchers began exploring both the theoretical foundations and practical implementations of quantum computers. They delved into the mathematics of quantum algorithms, the physics of qubit systems, and the engineering challenges of building quantum hardware. Significant advances were made in understanding how to manipulate quantum systems, leading to the development of qubits and experimental quantum devices. Fast forward to today, and the visions of Feynman and Deutsch are materializing in remarkable ways. Researchers and engineers around the globe are pushing the boundaries of what's computationally feasible, developing quantum technologies that were once purely theoretical. Companies leading the charge. Several major technology companies have invested heavily in quantum computing research and development. IBM, one of the pioneers in the field, IBM has developed a series of quantum processors, branded as IBM Quantum. They have made quantum computing accessible to researchers and the public through the IBM Quantum Experience, a cloud-based platform where users can run quantum algorithms on real quantum hardware. IBM's roadmap includes scaling up their quantum systems, improving error correction, and integrating quantum computing into broader computing environments. Google. In 2019, Google made headlines by announcing that its 53-qubit quantum processor, named Sycamore, had achieved quantum supremacy. This term refers to the point at which a quantum computer can perform a calculation that is practically impossible for a classical computer. Sycamore completed a specific task in 200 seconds that Google estimated would take the world's fastest supercomputer 10,000 years to complete. While the claim sparked debates, it was a significant milestone in demonstrating the potential of quantum computing. Microsoft. Microsoft is taking a unique approach by focusing on developing topological qubits, which are expected to be more stable and less prone to errors. They have created the Microsoft Quantum Development Kit and the QRAD programming language to advance quantum software development. Microsoft is investing in a full-stack approach, addressing everything from hardware to software and applications. Startups driving innovation. In addition to these tech giants, several startups are making significant contributions. Rigetti Computing. Based in Berkeley, California, Rigetti is developing superconducting qubit quantum computers and offers access to their systems through the cloud-based platform Forest. They focus on integrating quantum processors with classical computing infrastructure to create hybrid systems that can tackle complex problems. IonQ. Founded by leading academics in the field of trapped ion quantum computing, IonQ is leveraging trapped ion technology to build quantum computers with high-fidelity qubits and long coherence times. Their systems are accessible via cloud services like Amazon Braket and Microsoft Azure Quantum. Xanadu. A Canadian startup, Xanadu, is exploring photonic quantum computing using light particles as qubits. They aim to develop room temperature quantum computers that can be more easily integrated into existing technologies. Xanadu has also developed an open-source quantum machine learning library called PennyLane. Government initiatives. Governments around the world have recognized the strategic importance of quantum technologies and are investing in national initiatives. United States. The U.S. enacted the National Quantum Initiative Act in 2018, authorizing over $1 billion in funding for quantum research over 5 years. The initiative aims to enhance national security, economic competitiveness, and scientific leadership. European Union. The Quantum Flagship is a $1 billion, 10-year initiative launched by the EU to support quantum research and innovation. It brings together academic and industry partners to advance quantum technologies. China. China has made significant investments in quantum research, including the development of quantum communication satellites and the construction of the National Laboratory for Quantum Information Sciences. Australia, Canada, Japan, and others. Numerous countries have established quantum research centers and funding programs, recognizing the potential economic and technological benefits. The ongoing quest. The development of quantum computing is a complex and multidisciplinary endeavor. It involves understanding the deep principles of quantum mechanics, overcoming engineering challenges to build and maintain quantum hardware, and developing new algorithms and software to harness the power of quantum systems. Researchers are continually exploring new qubit implementations, such as superconducting qubits. As used by IBM and Google, these qubits operate at ultra-low temperatures and offer fast gate speeds but require sophisticated cooling systems. Trapped ions. IonQ and academic institutions use ions suspended in electromagnetic fields, manipulated with lasers, providing high-fidelity operations. Photonic qubits. Xanadu and others are exploring the use of photons, which can operate at room temperature and are less susceptible to environmental noise. Spin qubits. Utilizing the spin of electrons or nuclei in semiconductors, potentially allowing integration with existing semiconductor technology. Topological qubits. Microsoft's focus on these qubits aims to create systems inherently protected from certain types of errors, though realizing them experimentally remains a significant challenge. Challenges and opportunities. While progress has been substantial, significant challenges remain. Decoherence. Quantum states are delicate and can be easily disrupted by environmental interactions. Extending coherence times is crucial for practical computations. Error. Correction. Quantum error correction requires additional qubits and complex protocols to detect and correct errors without collapsing the quantum state. Scalability. Building systems with a large number of qubits while maintaining control and coherence is a major engineering hurdle. Software and algorithms. Developing quantum algorithms that can run on near-term hardware and provide practical advantages over classical algorithms is an ongoing area of research. Despite these challenges, the potential applications of quantum computing are vast. From solving complex optimization problems and advancing material science to enhancing artificial intelligence and securing communications through quantum cryptography, the possibilities are transformative. A collaborative future. The journey toward realizing the full potential of quantum computing is a collaborative effort. It involves not only physicists and engineers, but also computer scientists, mathematicians, chemists, and experts from various other fields. Cross-disciplinary collaboration accelerates innovation and helps address the multifaceted challenges involved. Educational institutions are expanding programs to train the next generation of quantum scientists and engineers. Governments, industries, and academia are forming partnerships to share knowledge, resources, and infrastructure. Moreover, international collaboration is vital. Quantum computing has global implications, and cooperative efforts can help ensure that the technology develops responsibly and benefits society as a whole. Conclusion. In reflecting on the visionary ideas of Richard Feynman and David Deutsch, we see how bold thinking and a willingness to challenge conventional paradigms can open up entirely new fields of exploration. Their insights laid the groundwork for a technological revolution that is still unfolding. Today, as we witness the rapid advancements in quantum computing, we are reminded of Feynman's and Deutsch's foresight. Their work continues to inspire researchers and innovators who are turning the once theoretical possibilities of quantum computing into reality. As we continue on this journey, it's an exciting time to be part of the unfolding story of quantum computing, a story that holds the promise of transforming our understanding of computation and unlocking solutions to some of the most complex problems facing humanity. Thank you for joining me in exploring the remarkable history and developments in quantum computing. The future is quantum, and together we're stepping into a new era of technological possibilities. Understanding how quantum computers work. So how do quantum computers actually work? At the core of quantum computing lies the concept of the qubit. Unlike a classical bit, which can be either a 0 or a 1, a qubit can exist in a state of 0, 1, or both at the same time, thanks to the principle of superposition. Imagine a sphere, and instead of being limited to the poles, representing 0 and 1, the qubit can exist at any point on the sphere's surface. This property allows quantum computers to process a vast amount of information simultaneously. Quantum computations are performed by manipulating these qubits using quantum gates. Think of quantum gates as the building blocks of quantum circuits, similar to logic gates in classical computing, but operating under the rules of quantum mechanics. These gates change the state of qubits in specific ways, enabling the quantum computer to perform complex calculations. One of the most fascinating aspects of quantum mechanics is entanglement, where qubits become linked and the state of one instantly influences the state of another, no matter how far apart they are. Because of superposition and entanglement, quantum gates can perform operations on multiple states at once. This capability, known as quantum parallelism, is what gives quantum computers their incredible potential to solve certain problems much more efficiently than classical computers. Physical implementations of qubits. Now let's delve into how we actually build these qubits. There are several physical implementations, each with its own advantages and challenges. 1. Superconducting qubits. First, we have superconducting qubits, which are used by companies like IBM and Google. These are tiny electrical circuits made from superconducting materials, metals that exhibit zero electrical resistance when cooled to temperatures near absolute zero. Because of their superconducting properties, these circuits can exhibit quantum behavior, acting as qubits. Superconducting qubits operate very quickly, which is excellent for computation speed. They can perform gate operations in nanoseconds, allowing for rapid calculations. Moreover, they can be fabricated using techniques similar to those used in semiconductor manufacturing, which is promising for scaling up the number of qubits. However, maintaining the ultra-cold temperatures required for superconductivity necessitates sophisticated refrigeration technology, making the systems complex and expensive. Additionally, superconducting qubits are susceptible to decoherence, meaning they can lose their quantum state due to interactions with the environment, typically within microseconds. Researchers are working on improving coherence times and error rates to make these systems more reliable. 2. Trapped ion qubits. Next, we have trapped ion qubits. This method involves trapping individual ions, charged atoms, in electromagnetic fields and manipulating them with laser beams. Companies like IonQ and various academic institutions are developing trapped ion technology. The advantages of trapped ion qubits include long coherence times, sometimes lasting seconds to minutes, which is significantly longer than superconducting qubits. This extended coherence allows for more complex computations without the quantum information degrading. Trapped ions also offer high-fidelity gate operations, meaning the errors in manipulating qubits are minimal. However, operations with trapped ions can be slower compared to superconducting qubits because manipulating ions with lasers and moving them into position takes time, typically in the microsecond to millisecond range. Scaling up the number of qubits is also challenging due to the complexity of controlling many ions simultaneously. 3. Photonic qubits. Then there's the approach of using photonic qubits, which utilize particles of light, photons, to carry quantum information. Photonic quantum computing allows for operations at room temperature and integrates well with existing fiber optic communication infrastructure. Startups like Xanadu are exploring this technology. Photonic qubits have the advantage of low decoherence, as photons don't easily interact with their environment, allowing them to maintain their quantum state over long distances. This makes them ideal for quantum communication applications. The challenge with photons is that they don't interact with each other naturally, making it difficult to implement two-qubit gates, which are essential for complex quantum computations. Researchers are developing methods to mediate interactions between photons, such as using nonlinear optical materials or integrating photons with other systems like quantum dots. 4. Spin qubits in semiconductors. Another promising approach involves spin qubits in semiconductors. This method uses the intrinsic spin property of electrons, or nuclei, in semiconductor materials to represent quantum information. Companies like Intel and academic institutions are researching this technology. Spin qubits can potentially leverage existing semiconductor manufacturing techniques, which is advantageous for scaling up production. They also operate at relatively higher temperatures compared to superconducting qubits, which could simplify cooling requirements. However, spin qubits face challenges with coherence times, as interactions with surrounding nuclear spins in the semiconductor lattice can cause decoherence. Precise control over individual electrons and their environment is also technically demanding. 5. Topological qubits. A more exotic approach is the development of topological qubits. This method aims to store quantum information in the global properties of a system, making it inherently protected from local disturbances and errors. It relies on manipulating quasi-particles known as Majorana zero modes, which can emerge in certain superconducting materials. Topological qubits could potentially offer much more robust quantum computing with significantly reduced error rates. However, this technology is still in the very early stages of research. Detecting and controlling Majorana particles is extremely challenging, and conclusive experimental evidence of their existence is still a subject of scientific investigation. Advancements in quantum error correction. One of the significant hurdles in quantum computing is dealing with errors. Quantum states are incredibly delicate and can be easily disrupted by interactions with the environment, a problem known as decoherence. Even tiny amounts of noise can cause errors in computations, which poses a substantial challenge for building reliable quantum computers. To overcome this, researchers are developing quantum error correction, QEC techniques. Unlike classical error correction, where a single bit error can be detected and corrected by redundancy, quantum error correction is more complex due to the no-cloning theorem, which states that quantum information cannot be copied. Quantum error correction involves encoding quantum information across multiple physical qubits to form a logical qubit that is more resistant to errors. One common method is the surface code, which arranges qubits in a two-dimensional lattice and can detect and correct errors through a series of measurements without collapsing the quantum information. Implementing QEC requires a significant number of additional qubits and sophisticated error detection and correction protocols, which increases the complexity and resource demands of quantum computers. Researchers are actively working on developing more efficient error correction codes and fault-tolerant architectures to make this process more practical for large-scale quantum computing. Pushing the boundaries of quantum computing. The quest to build scalable and practical quantum computers is a multifaceted endeavor involving physics, engineering, computer science, and materials science. Scientists and engineers are continuously pushing the boundaries, exploring new materials, technologies, and computational models to overcome the limitations of current quantum computing systems. Hybrid systems and quantum networking. Some researchers are working on hybrid systems that combine different types of qubits to leverage the strengths of each. For example, they might use superconducting qubits for fast processing and couple them with qubits that have longer coherence times for memory storage. Others are exploring quantum networking, where smaller quantum processors are connected via entanglement to form larger, distributed quantum computers. This approach could help overcome the scaling challenges by linking multiple quantum devices to work together on complex computations. Novel materials and approaches. There's also significant interest in discovering new materials and methods for quantum computing. Researchers are investigating two-dimensional materials like graphene, which have unique electronic properties that could be harnessed for quantum applications. Another area of exploration is using color centers in diamonds, such as nitrogen vacancy centers, which can act as qubits with long coherence times, even at room temperature. These systems could lead to practical quantum devices without the need for extreme cooling. Advances in quantum software and algorithms. While hardware development is crucial, advancing quantum software and algorithms is equally important. Programming quantum computers is fundamentally different from programming classical ones. So new languages, tools, and frameworks are being created to help developers write quantum code. Researchers are focusing on developing algorithms that can run efficiently on current and near-term quantum hardware, known as Noisy Intermediate Scale Quantum (NISQ) devices. They are also identifying practical applications where quantum computers can offer a real advantage over classical methods, such as in optimization, simulation, and machine learning tasks. The road ahead. As we continue to explore and innovate, the realization of quantum computers capable of solving classically intractable problems comes closer. The impact of such machines could be profound, potentially revolutionizing fields like cryptography, materials science, medicine, artificial intelligence, and more. However, there are still many challenges to overcome. Improving qubit coherence times, reducing errors, and scaling up the number of qubits are ongoing areas of research. Additionally, developing a skilled workforce capable of working with quantum technologies is essential for the industry's growth. Conclusion. In conclusion, the vision that Richard Feynman and David Deutsch had in the 1980s is steadily becoming a reality. By harnessing the unique properties of quantum mechanics, we're developing technologies that expand the boundaries of computation, opening up new frontiers of knowledge and possibility. The journey toward practical quantum computing is a collaborative effort, bringing together scientists, engineers, and innovators from around the world. While challenges remain, the progress made so far is remarkable, and the potential benefits are immense. As we stand on the cusp of this new era, it's an exciting time to witness the unfolding of quantum computing, a field that not only pushes the limits of technology, but also deepens our understanding of the fundamental laws of the universe. Thank you for joining me on this exploration of quantum computing, from its visionary beginnings to the cutting-edge developments of today. The future holds incredible possibilities, and I can't wait to see where this journey takes us next. As we delve deeper into the mechanics of quantum computing, it's important to understand the mathematical frameworks that underpin these technologies. Quantum algorithms are sets of instructions that leverage quantum principles to perform computations more efficiently than classical algorithms. One of the most famous is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. This has profound implications for cryptography, as much of modern encryption relies on the difficulty of factoring large numbers. Another significant algorithm is Grover's algorithm, which provides a quadratic speedup for unstructured search problems. While not exponential, this improvement is still highly valuable for a wide range of applications, from database searching to optimization problems. Quantum computing's potential extends across numerous industries, promising transformative impacts. One of the most promising areas where quantum computing could have a transformative impact is healthcare and pharmaceuticals. The process of drug discovery and development is incredibly complex, time-consuming, and expensive. Traditionally, it takes over a decade and billions of dollars to bring a new drug to market. This is largely because simulating molecular interactions, a critical step in understanding how a potential drug will behave, is computationally intensive. Classical computers often struggle with these simulations due to the sheer number of variables and the complexity of quantum mechanical interactions at the molecular level. Quantum computers, however, operate based on the same quantum principles that govern molecular interactions. This means they can simulate these interactions natively, providing precise models of complex molecules and chemical reactions. By accurately modeling molecular energy states, quantum computers can predict how a drug candidate will interact with its target, greatly increasing the efficiency of the drug discovery process. Take, for example, the challenge of understanding protein folding. Proteins are essential molecules in our bodies, and their function is determined by their three-dimensional structures, which result from a complex folding process. Misfolded proteins are associated with numerous diseases, including Alzheimer's, Parkinson's, cystic fibrosis, and many forms of cancer. Simulating protein folding is a monumental task for classical computers because the number of possible configurations grows exponentially with the size of the protein. Quantum computers could revolutionize this field by simulating protein folding processes accurately and efficiently. With this capability, scientists could understand the mechanisms of diseases at a molecular level, leading to the development of targeted therapies and personalized medicine. Imagine being able to design a drug that fits a protein like a key in a lock, effectively neutralizing a disease-causing agent with minimal side effects. Moreover, quantum computing could aid in genomics and genetic analysis. Sequencing and analyzing genomes involves handling massive amounts of data. Quantum algorithms could process this data faster, identifying genetic markers associated with diseases and enabling early intervention. Personalized treatment plans based on an individual's genetic makeup could become a reality, ushering in a new era of precision medicine. In the realm of vaccine development, the recent COVID-19 pandemic has highlighted the need for rapid response to emerging health threats. Quantum computers could accelerate the identification of potential vaccine candidates by modeling viral protein structures and predicting how they might mutate. This proactive approach could help us stay ahead of pandemics, saving countless lives. But the benefits of quantum computing in healthcare aren't limited to drug discovery. They extend to optimizing healthcare operations. Hospitals and clinics generate vast amounts of data related to patient records, treatment outcomes, and resource management. Quantum algorithms could analyze this data to improve patient care, predict resource needs, and streamline administrative processes. Transitioning to the financial sector, quantum computing holds the promise of transforming how we manage risk, optimize portfolios, and detect fraudulent activities. Financial markets are inherently complex, influenced by a multitude of variables such as economic indicators, political events, and investor behaviors. Traditional models often rely on simplifications and assumptions that can limit their accuracy. Quantum computers can process and analyze enormous datasets simultaneously, identifying subtle patterns and correlations that classical computers might miss. For instance, in portfolio optimization, investors seek to balance risk and return by selecting a mix of assets that aligns with their investment goals. Quantum algorithms can evaluate a vast number of possible asset combinations in a fraction of the time it would take a classical computer, identifying the optimal portfolio with greater precision. Risk management is another area ripe for quantum innovation. Banks and financial institutions need to assess the potential risks associated with loans, investments, and market fluctuations. Quantum computing could enhance the modeling of complex financial instruments and derivatives, providing more accurate assessments of potential exposures. Consider the problem of Monte Carlo simulations, a statistical technique used extensively in finance to model the probability of different outcomes in processes that involve random variables. These simulations require generating and analyzing a large number of scenarios to predict future states of the market. Quantum computers can significantly speed up Monte Carlo simulations using algorithms like the quantum amplitude estimation algorithm, providing faster and more precise insights into market dynamics and investment risks. Fraud detection is also a critical concern in the financial industry. As financial transactions become increasingly digital, the potential for fraudulent activities grows. Quantum machine learning algorithms could analyze transaction data in real time, identifying anomalies and patterns indicative of fraud more effectively than classical methods. Moreover, quantum computing could enhance cybersecurity measures within the financial sector. While there's a risk that quantum computers could break current encryption methods, they can also be used to develop new quantum-resistant encryption protocols, securing sensitive financial data against future threats. In logistics and supply chain management, the complexity of optimization problems increases exponentially with the number of variables involved. Companies aim to minimize costs and maximize efficiency by optimizing routes for delivery vehicles, managing inventory levels, and scheduling operations. Classical algorithms struggle with these large-scale optimization problems due to the combinatorial explosion, the rapid increase in possible solutions as the number of variables grows. Quantum computers are particularly well-suited to tackle these types of problems. For example, the Quantum Approximate Optimization Algorithm, QAOA, is designed to find approximate solutions to combinatorial optimization problems efficiently. A global shipping company could use a quantum computer to optimize its fleet's routing by simultaneously considering a multitude of factors: weather conditions, traffic patterns, fuel consumption, delivery deadlines, vehicle capacities, and even real-time data from IoT devices. By processing all these variables at once, quantum algorithms can identify the most efficient routes, reducing transit times and fuel costs. This not only leads to significant cost savings, but also reduces carbon emissions, contributing to environmental sustainability. In an industry where margins are tight and efficiency is paramount, such improvements can provide a substantial competitive advantage. Building on the transformative potential of quantum computing in logistics and supply chain management, let's delve deeper into how it could revolutionize inventory management. For many companies, balancing the cost of holding inventory against the risk of stockouts is a perpetual challenge. Holding too much inventory ties up capital and incurs storage costs, while too little can lead to missed sales opportunities, dissatisfied customers, and damage to the brand's reputation. Traditional inventory management systems rely on forecasting models that often can't account for the sheer complexity and variability of market dynamics. These models may use historical sales data and simple statistical methods to predict future demand, but they struggle to incorporate the multitude of factors that influence purchasing behavior, such as sudden shifts in consumer preferences, seasonal trends, economic indicators, and unforeseen events like natural disasters or pandemics. Quantum computing offers a powerful tool to address these challenges. By leveraging quantum algorithms, companies could analyze vast amounts of data simultaneously, including real-time sales figures, social media sentiment, competitor pricing, supply chain disruptions, and macroeconomic trends. Quantum computers can process this multidimensional data much more efficiently than classical computers, identifying intricate patterns and correlations that were previously inaccessible. Imagine a global retailer using quantum computing to optimize inventory levels across thousands of products and hundreds of locations. The quantum algorithms could help determine the optimal stock for each item in each store, considering local demand patterns, upcoming promotions, and even weather forecasts that might influence purchasing behavior. This would ensure that products are available when and where customers want them, reducing lost sales due to out-of-stock items while minimizing excess inventory that ties up capital and incurs storage costs. Moreover, quantum computing could enable dynamic inventory management, allowing companies to adjust inventory levels in real time. For example, if a sudden trend emerges on social media causing a spike in demand for a particular product, quantum algorithms could quickly analyze the situation and recommend immediate actions, such as reallocating stock from other locations, expediting orders from suppliers, or adjusting pricing strategies. Additionally, quantum computing could enhance supply chain transparency. By tracking products from suppliers through to the end customer, companies could gain real-time visibility into their supply chains. Quantum algorithms could analyze this data to predict potential bottlenecks or delays, enabling proactive measures to mitigate disruptions. Moving beyond inventory, quantum computing could revolutionize manufacturing processes through optimized scheduling and resource allocation. Manufacturing involves coordinating numerous variables: machinery availability, workforce scheduling, raw material supply, maintenance schedules, and production deadlines. The goal is to maximize efficiency and productivity while minimizing costs and downtime. Classical computing methods often rely on simplified models or heuristics that can't capture the full complexity of these interrelated factors, leading to suboptimal decisions. Quantum computers, however, can handle the combinatorial complexity of manufacturing optimization problems by evaluating countless possibilities simultaneously. Consider a large automotive manufacturer producing multiple vehicle models on shared assembly lines. The production schedule must account for varying assembly times, component availability, labor shifts, and maintenance windows. Quantum algorithms could process all these variables in parallel to generate an optimized production schedule that maximizes throughput, minimizes idle time, and ensures timely delivery. Moreover, quantum computing could improve resource allocation by optimizing the use of materials and energy. For example, in a process-intensive industry like chemical manufacturing, quantum algorithms could optimize reaction conditions and resource inputs to increase yields and reduce waste. Predictive maintenance is another area where quantum computing could make a significant impact. By analyzing data from sensors embedded in machinery, such as temperature, vibration, and acoustic emissions, quantum algorithms could predict equipment failures before they occur. This proactive approach allows maintenance to be scheduled at the most opportune times, reducing unplanned downtime, extending equipment life, and saving costs associated with emergency repairs. In the era of Industry 4.0, manufacturing is becoming increasingly interconnected, with smart factories leveraging automation, IoT devices, and real-time data analytics. Quantum computing could accelerate this transformation by providing the computational power necessary to analyze vast amounts of data and optimize complex systems in real time. The implications of quantum computing extend to urban planning and the development of smart cities. As urban populations continue to grow, cities face mounting challenges related to traffic congestion, energy consumption, waste management, and the efficient delivery of public services. The integration of IoT devices and sensors throughout urban environments generates enormous amounts of data, presenting both an opportunity and a challenge for city planners. Traffic flow optimization is a prime example. Traditional traffic management systems use fixed timing for traffic signals and rely on reactive measures to address congestion. Quantum algorithms could analyze real-time data from traffic cameras, GPS devices, public transportation schedules, and even social events to optimize traffic signal timings dynamically. By considering all these variables simultaneously, quantum computers could reduce congestion, shorten commute times, and decrease emissions from idling vehicles. In public transportation, quantum computing could optimize routes and schedules based on passenger demand patterns, leading to more efficient and responsive services. For instance, bus and train frequencies could be adjusted in real time to accommodate fluctuations in ridership, ensuring that resources are allocated where they're needed most. Energy distribution networks present another area ripe for optimization. With the increasing integration of renewable energy sources like solar and wind power, which are variable and less predictable, balancing supply and demand becomes more complex. Quantum algorithms could process data from millions of smart meters, weather forecasts, and energy storage systems to optimize the distribution of electricity across the grid. This could reduce energy waste, lower costs for consumers, and enhance the stability and resilience of the power supply. Furthermore, quantum computing could enhance waste management systems by optimizing collection routes, predicting waste generation patterns, and improving recycling processes. By analyzing data from smart bins and environmental sensors, cities could reduce operational costs and minimize their environmental impact. In the realm of emergency services, quantum algorithms could improve response times by optimizing the allocation and dispatch of resources. By analyzing data such as emergency call locations, traffic conditions, and hospital capacities, quantum computers could recommend the fastest routes in appropriate facilities, potentially saving lives. In the context of global supply chains, quantum computing could help companies navigate the intricate complexities of international trade, tariffs, regulatory compliance, and geopolitical risks. Supply chains today are highly interconnected and globalized, involving a vast network of suppliers, manufacturers, logistics providers, and retailers spread across multiple countries and regions. Quantum computing can enable companies to model their entire supply chain as a complex system, capturing the interdependencies and variability inherent in global operations. By simulating different scenarios, quantum algorithms can help businesses identify vulnerabilities and optimize their supply chain strategies. For example, companies can use quantum computing to assess the impact of varying tariffs and trade policies on sourcing decisions. By analyzing a multitude of factors, including cost, lead times, quality, and political stability, quantum algorithms can recommend the optimal mix of suppliers and manufacturing locations to minimize costs and risks. In the face of supply chain disruptions, such as those caused by natural disasters, pandemics, or geopolitical tensions, Quantum computing can provide rapid analysis and response strategies. Companies could simulate the effects of a port closure, a supplier shutdown, or a sudden surge in demand, allowing them to adjust their operations proactively. This agility enhances resilience and can provide a competitive advantage in volatile markets. Regulatory compliance is another complex area where quantum computing can assist. Companies operating internationally must navigate a labyrinth of regulations related to trade, labor laws, environmental standards, and product safety. Quantum algorithms could analyze regulatory requirements across different jurisdictions, ensuring that products and processes comply with all applicable laws. This reduces the risk of legal penalties, delays, and reputational damage. Furthermore, quantum computing could optimize logistics and routing on a global scale. By considering variables like shipping costs, transit times, fuel prices, weather conditions, and customs procedures, quantum algorithms can determine the most efficient and cost-effective shipping routes. This optimization reduces delivery times, lowers transportation costs, and minimizes the environmental impact through reduced emissions. In terms of sustainability, quantum computing can help companies meet their environmental goals by optimizing resource usage and reducing waste throughout the supply chain. For instance, quantum algorithms can assist in designing packaging that minimizes material usage while protecting products, or in planning production schedules that reduce energy consumption. In conclusion, the integration of quantum computing into various sectors offers transformative potential. In inventory management, it enables precise demand forecasting and real-time adjustments, reducing costs and improving customer satisfaction. In manufacturing, it optimizes scheduling and resource allocation, enhances predictive maintenance, and supports flexible production strategies. In the development of smart cities, quantum computing addresses the complex challenges of urbanization by optimizing traffic flow, energy distribution, waste management, and emergency services, leading to more livable and sustainable urban environments. In global supply chains, it provides the computational power to navigate complexities, enhance resilience, ensure compliance, and promote sustainability. These advancements are not without challenges. The practical implementation of quantum computing requires continued progress in hardware development, error correction, and algorithm design. Additionally, businesses and governments must invest in the necessary infrastructure and develop the expertise to harness these technologies effectively. As we move forward, collaboration between industry leaders, researchers, policymakers, and educators will be essential. By fostering partnerships and sharing knowledge, we can accelerate the adoption of quantum computing and maximize its benefits for society. Thank you for joining me on this exploration of the profound ways quantum computing could reshape industries and improve lives. The future holds exciting possibilities, and together we can embrace the opportunities that quantum technology presents to build a more efficient, responsive, and sustainable world. In all these sectors, healthcare, finance, logistics, the common thread is the ability of quantum computing to handle complexity at a scale and speed unattainable by classical computers. This opens up new possibilities for innovation, efficiency, and problem solving. However, it's important to acknowledge the challenges that come with integrating quantum computing into these industries. Quantum hardware is still in its developmental stages, and building quantum computers with enough qubits to solve practical, real-world problems remains a significant technical hurdle. Error rates, qubit coherence, and scalability are ongoing concerns that researchers are actively working to address. Additionally, there are considerations around the cost of quantum computing resources, the need for specialized expertise, and the development of quantum algorithms tailored to specific industry needs. Collaboration between quantum computing companies, industry leaders, academic institutions, and government agencies will be crucial in overcoming these challenges. In conclusion, quantum computing holds immense potential to transform healthcare by accelerating drug discovery and personalized medicine, to revolutionize finance through enhanced risk management and optimization, and to optimize logistics and supply chain management for greater efficiency and sustainability. As we continue to explore and develop this groundbreaking technology, we stand on the brink of a new era where the boundaries of what we can achieve are expanded beyond our current imagination. Thank you for joining me on this deep dive into the transformative potential of quantum computing across these critical industries. Together, let's look forward to a future where quantum technology helps us solve some of the most complex challenges and improves lives around the world. In the realm of energy, quantum computing could enhance the modeling of complex systems such as electrical grids, leading to more efficient energy distribution and the integration of renewable energy sources. Accurate modeling of materials at the quantum level could also lead to the development of better batteries and superconductors, advancing energy storage and transmission technologies. Climate modeling is another area where quantum computing could make a significant impact. Earth's climate system involves a vast number of interacting components, from atmospheric dynamics to ocean currents and biosphere interactions. Quantum computers could process these complex variables simultaneously, providing more accurate models that could inform policy decisions and climate intervention strategies. Artificial intelligence and machine learning stand to benefit greatly from quantum computing. Quantum machine learning algorithms could handle higher dimensional data spaces and complex patterns more efficiently, leading to advances in image and speech recognition, natural language processing, and predictive analytics. This could accelerate the development of smarter, more adaptable AI systems capable of solving problems beyond the reach of current technology. Despite these exciting prospects, significant challenges remain in bringing quantum computing to practical fruition. Decoherence is a fundamental obstacle. Quantum states are fragile and can be easily disrupted by interactions with the environment, causing the loss of quantum information. Maintaining qubits in a coherent state long enough to perform meaningful computations requires isolating them from all forms of interference, which is technically demanding. To address this, researchers are developing quantum error correction techniques. These methods involve encoding quantum information across multiple physical qubits to form a single logical qubit that is more robust against errors. However, this comes at the cost of requiring many more qubits, increasing the complexity and resource demands of quantum computers. Scalability is another major challenge. Building a quantum computer with a sufficient number of qubits to outperform classical computers on practical tasks, achieving what's known as quantum supremacy or quantum advantage, is a daunting engineering feat. Each additional qubit increases the difficulty of controlling the system and managing errors. Researchers are exploring modular and networked approaches, where smaller quantum processors are linked together to form a larger system. The cost of developing and maintaining quantum hardware is currently high, limiting accessibility. Specialized facilities, extreme operating conditions, such as ultra-low temperatures for superconducting qubits, and complex control systems contribute to the expense. As the technology matures, economies of scale and technological innovations may reduce costs, but significant investment is still required. Ethical and security concerns also arise with the advent of quantum computing. The ability to break current encryption methods poses a threat to global data security, including financial transactions, personal communications, and national security information. Preparing for this eventuality requires the development and implementation of post-quantum cryptography, encryption methods that are resistant to quantum attacks. Furthermore, the potential for technological disparity between nations raises geopolitical concerns. Countries that achieve significant advancements in quantum computing could gain substantial economic and strategic advantages. This has led to a global race, with significant investments from governments and private sectors worldwide. To mitigate these risks, international cooperation and agreements on the ethical use of quantum technology are essential. Collaborative efforts can promote responsible development, ensure that benefits are shared globally, and prevent the misuse of quantum computing capabilities. As we look to the future, education and workforce development will play critical roles. There's a growing need for professionals skilled in quantum physics, computer science, engineering, and related fields. Universities and educational institutions are beginning to offer specialized programs in quantum information science to prepare the next generation of innovators. Public awareness and engagement are also important. Understanding the basics of quantum computing and its potential impacts can help society make informed decisions about the adoption and regulation of this technology. Open dialogues about ethical considerations, privacy concerns, and societal implications will be crucial as quantum computing becomes more prevalent. In terms of technological advancements, researchers are exploring new frontiers in quantum technology beyond computing. Quantum communication leverages entanglement to create secure communication channels. Quantum sensing uses quantum states to measure physical quantities with extreme precision, which could have applications in navigation, medical imaging, and material science. Moreover, hybrid approaches that combine quantum and classical computing are emerging. In these systems, quantum processors handle specific tasks that are well suited to quantum computation, while classical processors manage the overall workflow. This synergistic approach could accelerate the practical adoption of quantum computing by leveraging existing classical infrastructure. As quantum computing continues to evolve, we may see the development of quantum networks, the quantum equivalent of the internet. These networks would enable quantum computers to communicate and share information securely, opening up possibilities for distributed quantum computing and new applications we have yet to imagine. The potential societal impacts of quantum computing are vast. In medicine, personalized treatments based on individual genetic makeup could become the norm, improving outcomes and reducing side effects. In environmental science, better modeling and resource management could help us address pressing issues like pollution and resource depletion. In economics, quantum computing could lead to more efficient markets, improved economic forecasting, and new financial instruments tailored to individual needs. In governance, data analysis and modeling could enhance policymaking, emergency response, and infrastructure planning. However, with these advancements come responsibilities. Ensuring equitable access to quantum technologies is essential to prevent widening the gap between developed and developing regions. Ethical frameworks need to be established to guide research and application, preventing misuse and protecting individual rights. As we stand on the threshold of the quantum computing era, one aspect demands our immediate attention: privacy. Quantum computing's immense power to process and analyze vast data sets at unprecedented speeds holds incredible promise, but it also brings significant privacy concerns. Imagine a world where every digital footprint you've ever made, every online purchase, every social media interaction, every medical record could be analyzed instantaneously to reveal intimate details about your behavior, preferences, and even your thoughts. This isn't science fiction, it's a potential reality we must prepare for. Quantum computers, with their ability to break current encryption methods, could de-anonymize data and construct detailed profiles of individuals. The encryption that protects our emails, bank accounts, and personal communications could become obsolete, exposing sensitive information to unauthorized access. To safeguard privacy in the age of quantum computing, robust legal frameworks and technological innovations are essential. Governments and organizations must work together to update data protection laws, like the European Union's General Data Protection Regulation, to address quantum threats. This includes mandating the use of quantum-resistant encryption algorithms, new cryptographic methods designed to withstand quantum attacks. Technologically, we need to invest in developing and implementing these quantum-safe encryption techniques. Initiatives like the National Institute of Standards and Technology's efforts to standardize post-quantum cryptography are critical steps forward. Quantum key distribution, which uses the principles of quantum mechanics to securely exchange encryption keys, offers another layer of protection. Any attempt to intercept these keys would alter their state and alert the parties involved, ensuring secure communication. But technology and laws aren't yet enough. Ethical considerations must guide our approach. Organizations developing quantum technologies should be transparent about how they're using data. Individuals should have control over their personal information, with clear options to consent or opt out of data collection and analysis. Accountability mechanisms are necessary to hold entities responsible for data misuse or breaches. Public awareness plays a vital role. By educating ourselves about quantum computing and its implications, we can make informed choices and advocate for policies that protect our privacy. This leads us to another crucial aspect: education. Integrating quantum concepts into education at all levels is essential to prepare the next generation for the quantum future. By introducing these ideas early on, we demystify the subject and inspire interest. In primary and secondary schools, simplified explanations of quantum phenomena can spark curiosity. Interactive activities, like simple experiments with light or quantum games, can make learning engaging and accessible. At the university level, comprehensive curricula should cover quantum mechanics, quantum computing, and their applications, even for students not majoring in physics. Interdisciplinary courses that combine quantum physics with computer science, ethics, and social sciences encourage a holistic understanding of the quantum world. This interdisciplinary approach is vital because the challenges and opportunities presented by quantum computing aren't confined to a single field. Teacher training and resources are critical to this educational effort. Educators need support through professional development programs, workshops, and access to quality teaching materials. Collaboration between schools, universities, and research institutions can provide valuable expertise in resources. Hands-on experience enhances learning. Quantum simulators and cloud-based access to real quantum computers allow students to experiment and understand quantum principles in practice. Learning quantum programming languages like Qiskit or Cirq equips students with the skills needed to work with quantum technologies. Ethics and social implications should be integral parts of the curriculum. Discussions about privacy concerns, societal impacts, and security issues help students grasp the broader context of quantum computing. Encouraging diversity and inclusion in these programs ensures a wide range of perspectives and fosters innovation. But education and privacy protection efforts can't succeed in isolation. International collaboration is vital. Quantum computing has the potential to address global challenges that transcend borders. Climate change, pandemics, cybersecurity threats, all of which require coordinated international responses. Let's consider one of the most pressing challenges of our time: climate change. The Earth's climate system is an incredibly complex web of interactions involving the atmosphere, oceans, land surfaces, ice masses, and biosphere. It is influenced by a myriad of factors, including solar radiation, greenhouse gas concentrations, volcanic activity, human-induced emissions, and feedback mechanisms that can amplify or dampen changes. Accurately modeling this intricate system is essential for predicting future climate scenarios, assessing the impact of mitigation strategies, and informing policy decisions. However, current climate models are limited by the computational power of classical supercomputers. These models must often simplify or approximate certain processes to make the calculations tractable, which can reduce the precision of predictions. For instance, simulating cloud formation, aerosol interactions, and small-scale turbulence involves complex calculations that are computationally intensive. This is where quantum computing could revolutionize climate science. Quantum computers have the potential to process vast amounts of data and perform complex calculations at speeds unattainable by classical computers. By leveraging qubits that can exist in multiple states simultaneously, quantum computers can handle the enormous data sets and intricate equations required for high-resolution climate modeling. Imagine being able to simulate the Earth's climate system with unprecedented detail, capturing the nuanced interactions between atmospheric particles, ocean currents, and biosphere feedbacks. Quantum computing could enable models that account for quantum-level interactions in chemical processes, such as the formation and breakdown of greenhouse gases. This level of detail could lead to more accurate predictions of temperature changes, sea level rise, extreme weather events, and other critical factors. With these enhanced models, scientists and policymakers could better assess the effectiveness of various mitigation strategies, such as reducing carbon emissions, implementing geoengineering techniques, or preserving natural carbon sinks like forests and wetlands. This would facilitate more informed decision-making and resource allocation, ultimately leading to more effective actions against climate change. However, to fully harness the potential of quantum computing and climate modeling, international collaboration is essential. Climate change is a global issue that transcends national borders, and no single country has all the necessary data, resources, or expertise to tackle it alone. Sharing data from satellites, ocean buoys, weather stations, and other monitoring systems worldwide enriches the data sets used in climate models, improving their accuracy. Moreover, collaborative efforts allow for the pooling of resources, such as quantum computing facilities and expertise. Developing and maintaining quantum computers is expensive and technologically demanding. By working together, countries can share these costs and benefits, accelerating progress. Joint research initiatives can bring together the brightest minds from different nations, fostering innovation and breakthroughs that might not occur in isolation. International collaboration also helps ensure that advancements in climate modeling benefit all countries, especially those most vulnerable to the impacts of climate change, such as small island nations and developing countries. By sharing knowledge and tools, we can support global adaptation and mitigation efforts, promoting equity and sustainability. In the realm of healthcare, quantum computing holds the promise of transforming how we develop drugs and respond to health crises like pandemics. The process of drug discovery is notoriously time-consuming and costly. It often involves screening millions of compounds to find potential candidates, followed by extensive testing to assess their safety and efficacy. This process can take over a decade and cost billions of dollars. A significant bottleneck in drug discovery is the accurate simulation of molecular interactions. Molecules interact at the quantum level, and understanding these interactions is crucial for designing effective drugs. Classical computers struggle with these simulations due to the complexity of quantum mechanical calculations, especially for large molecules with many electrons. Quantum computers, operating on the principles of quantum mechanics, are naturally suited to simulate these molecular systems. They can handle the complex calculations required to model the behavior of electrons in molecules, predict how molecules will interact with biological targets, and identify promising drug candidates more efficiently. For example, during the development of a new medication, quantum computers could simulate how a drug molecule binds to a protein associated with a disease, identifying the most effective compounds with fewer trials. This could drastically reduce the time and cost required to bring new drugs to market. In the context of a pandemic, such as COVID-19, this capability becomes even more critical. Rapidly developing effective treatments and vaccines is essential to saving lives and controlling the spread of the disease. Quantum computing could accelerate the identification of potential antiviral compounds or vaccine targets by simulating viral proteins and their interactions with human cells. Moreover, quantum computing could enhance genomic analysis. Sequencing and analyzing genetic material is vital for understanding viruses and their mutations, which can impact vaccine effectiveness. Quantum algorithms could process genetic data faster and more accurately, aiding in monitoring viral evolution and adapting vaccines accordingly. Once again, international cooperation is vital in realizing these benefits. Pandemics are global by nature, and pathogens can spread rapidly across borders. Sharing data, such as genetic sequences of viruses, patient outcomes, and epidemiological information, is crucial for a coordinated response. Collaborative research allows scientists from different countries to pool their expertise and resources, accelerating the development of treatments and vaccines. For instance, during the COVID-19 pandemic, unprecedented international collaboration led to the rapid development of multiple vaccines in record time. Equitable access to medical advancements is also a significant concern. Without international agreements and cooperation, there is a risk that only wealthier nations will benefit from new treatments and technologies, leaving vulnerable populations behind. Efforts like the COVAX initiative aim to ensure that vaccines are distributed fairly worldwide. In the context of quantum-assisted healthcare advancements, similar cooperative frameworks will be necessary to promote global health equity. Now let's dive into the fascinating and somewhat daunting world of cybersecurity in the age of quantum computing. This is a topic that affects all of us, whether we're tech enthusiasts or just everyday users of digital devices. The rise of quantum computing brings with it incredible opportunities, but it also presents significant challenges that we need to address proactively. One of the most pressing concerns revolves around the security of our digital communications. You might be wondering, what's the big deal? Well, the encryption methods we currently use to protect everything from personal emails and bank transactions to government communications are based on mathematical problems that are incredibly tough for classical computers to solve. These encryption algorithms, like RSA and ECC, elliptic curve cryptography, rely on the difficulty of tasks such as factoring large prime numbers or calculating discrete logarithms. Essentially, they're puzzles that would take a classical computer an impractical amount of time to crack, so our information stays safe. However, quantum computers operate on a whole different level. They leverage the principles of quantum mechanics to process information in ways that classical computers can't. One of the game changers here is Shor's algorithm, a quantum algorithm developed by mathematician Peter Shor in 1994. This algorithm can efficiently solve the very mathematical problems that current encryption methods depend on for security. What does this mean in practical terms? Imagine a quantum computer powerful enough to run Shor's algorithm on large numbers. Such a computer could potentially break the encryption that secures our digital world. Personal emails, online banking, confidential business communications, government secrets, all could be at risk of exposure. It's like having the master key that can unlock any digital lock. The possibility of such vulnerabilities isn't just a theoretical concern, it's a global issue that could have far-reaching consequences. Cybersecurity threats facilitated by quantum computing could disrupt economies by undermining the financial systems we rely on. They could compromise national security by exposing sensitive government information. Moreover, they could erode public trust in digital systems, which are integral to modern life, from healthcare and transportation to energy grids and communication networks. Given the magnitude of this challenge, developing and implementing quantum-resistant encryption, also known as post-quantum cryptography, has become an urgent priority. But this isn't a straightforward task. Creating new encryption standards that can withstand quantum attacks is a complex endeavor that goes beyond simple upgrades or patches. First off, it requires us to explore new mathematical problems that are resistant to both classical and quantum attacks. Researchers are investigating areas like lattice-based cryptography, hash-based cryptography, code-based cryptography, and multivariate quadratic equations. Each of these potential solutions comes with its own set of challenges and requires rigorous testing to ensure they can provide the level of security we need. Developing these new encryption methods demands collaboration on a global scale. Cryptographers, mathematicians, computer scientists, and quantum physicists from all over the world are working together to tackle this issue. No single organization or country has all the expertise or resources needed to address this challenge alone. It's a multidisciplinary effort that benefits from diverse perspectives and shared knowledge. Furthermore, once these new encryption algorithms are developed, they need to be standardized and adopted widely. This involves international bodies like the National Institute of Standards and Technology, NIST, in the United States, which is already running a process to evaluate and standardize post-quantum cryptographic algorithms. The goal is to create encryption methods that can be seamlessly integrated into existing systems and that everyone can trust. But the transition to quantum-resistant encryption isn't just about the technical aspects. It also requires careful planning and coordination. Think about all the devices and systems that use encryption, from smartphones and laptops to servers and cloud services. Updating them to use new encryption standards is a massive logistical undertaking. It involves software updates, hardware considerations, and ensuring compatibility across different platforms and devices. There's also the human element to consider. Organizations need to educate their employees and stakeholders about the changes. Governments need to develop policies and regulations to support the transition. Users need to understand why these changes are happening and what they mean for their privacy and security. On the brighter side, the rise of quantum computing doesn't spell doom for cybersecurity. In fact, it also brings opportunities to enhance security. Quantum technologies can be used to develop new methods of securing information. For example, quantum key distribution, QKD, uses the principles of quantum mechanics to create secure communication channels. In QKD, any attempt to eavesdrop on the key exchange would disturb the quantum states involved, alerting the communicating parties to the presence of an intruder. Moreover, the push toward quantum-resistant encryption can lead to overall improvements in our security infrastructure. It's an opportunity to reassess our current systems, identify existing vulnerabilities, and implement more robust security measures. This proactive approach can make our digital world safer, not just against quantum threats, but against a range of cyber risks. In addition, quantum computing can aid in enhancing cybersecurity tools. Quantum algorithms can improve machine learning models used in threat detection, enabling faster and more accurate identification of cyber attacks. This means we could respond more quickly to threats, minimizing potential damage. However, to fully realize these opportunities and mitigate the risks, international cooperation is crucial. Cybersecurity is a global concern, and quantum computing transcends national borders. Collaborative efforts allow us to pool resources, share expertise, and develop standardized solutions that benefit everyone. Organizations like the Global Commission on the Stability of Cyberspace and the World Economic Forum are examples of platforms where such international collaboration can take place. By working together, countries can establish norms and agreements on the responsible development and use of quantum technologies, preventing a cybersecurity arms race and promoting peace and stability. Furthermore, fostering a culture of collaboration extends to the private sector and academia. Tech companies, research institutions, and universities are at the forefront of quantum research and development. Partnerships between these entities can accelerate innovation and ensure that advancements in quantum computing are aligned with societal needs and ethical considerations. In conclusion, while the rise of quantum computing presents significant challenges to our current cybersecurity frameworks, it also offers a pathway to stronger, more resilient systems. By acknowledging the potential risks and proactively working to address them, we can safeguard our digital infrastructure against future threats. It's a pivotal moment in the evolution of technology. The decisions we make now will have lasting impacts on the security and integrity of our digital world. By embracing collaboration, investing in research, and promoting awareness, we can navigate the quantum future with confidence. So let's view quantum computing not just as a looming threat, but as a catalyst for innovation in cybersecurity. Together, we can build a secure digital landscape that stands the test of time and technological advancement, ensuring that the benefits of the quantum revolution are realized safely and equitably for all. International collaboration is crucial for several reasons. Standardization. To ensure global security, new encryption methods need to be standardized and adopted worldwide. International bodies like the International Organization for Standardization, ISO, and the Internet Engineering Task Force, IETF, play vital roles in developing and promoting these standards. Collaborative efforts help ensure that the standards are robust, thoroughly vetted, and widely accepted. Research and development. Sharing knowledge about vulnerabilities, potential attack vectors, and defensive strategies accelerates the development of effective solutions. Joint research initiatives and open communication among experts enhance the collective understanding of quantum threats and how to mitigate them. Implementation. Transitioning global infrastructure to quantum-resistant encryption is a massive undertaking. Coordinated efforts can help synchronize this transition, preventing weak links in the global communication network that could be exploited. Ethical considerations. International cooperation can help establish norms and agreements regarding the use of quantum computing and cybersecurity, promoting responsible use and discouraging malicious activities. Additionally, quantum technologies offer opportunities to enhance cybersecurity through methods like quantum key distribution, QKD. QKD uses the principles of quantum mechanics to securely distribute encryption keys. Any attempt to intercept the keys alters their quantum state, alerting the communicating parties to the presence of an eavesdropper. Implementing QKD on a global scale requires international collaboration to build the necessary infrastructure and ensure interoperability between systems. Countries and organizations must work together to develop and deploy these technologies, share best practices, and provide support to nations that may lack the resources to implement them independently. This collective effort helps protect the integrity of international communications, financial systems, and critical infrastructure, benefiting all participants. In all these areas, climate change, healthcare, and cybersecurity, the underlying message is clear. Global challenges require global solutions. Quantum computing has the potential to be a powerful tool in addressing these challenges, but its benefits can only be fully realized through international collaboration. By sharing data, resources, and expertise, we can accelerate innovation, avoid duplication of efforts, and ensure that advancements benefit everyone. Collaborative frameworks help distribute the advantages of quantum computing equitably, prevent technological disparities, and promote global stability. However, fostering international collaboration also involves overcoming obstacles such as geopolitical tensions, competition for technological dominance, and concerns over intellectual property rights. Building trust through transparency, open communication, and mutual respect is essential. Establishing international agreements and organizations dedicated to quantum technology can facilitate cooperation. These entities can set shared goals, establish ethical guidelines, and provide platforms for collaboration. Educational exchanges, joint research projects, and multinational conferences also help build networks and foster a spirit of partnership. In conclusion, as we navigate the opportunities and challenges presented by quantum computing, embracing international collaboration is not just beneficial, it's imperative. By working together, we can harness the full potential of quantum technologies to tackle some of the most critical issues facing humanity, building a safer, healthier, and more sustainable future for all. International collaboration brings numerous benefits. By pooling resources, we can accelerate research and development, avoid duplication of efforts, and ensure that advancements are compatible and interoperable worldwide. Knowledge sharing fosters innovation and helps establish global standards. However, collaboration isn't without challenges. Geopolitical tensions, competition for technological supremacy, and concerns over intellectual property rights can hinder cooperation. Disparities in funding and infrastructure between developed and developing countries can also create imbalances. To overcome these obstacles, we need strategies that promote effective collaboration. International agreements and treaties can outline shared goals, ethical guidelines, and frameworks for cooperation. Establishing multinational research centers where scientists from different countries work side by side can foster trust and mutual understanding. Educational exchanges play a significant role as well. By facilitating student and faculty exchanges, we build cross-cultural connections and networks that can drive collaborative efforts. Open science practices, like publishing research findings in open access journals, ensure that knowledge is accessible to all, regardless of geographical location. International organizations can facilitate these collaborations. The United Nations can promote policies that encourage cooperation, while organizations like the World Economic Forum provide platforms for public-private partnerships on global issues, including quantum technology. Addressing global disparities is essential. Supporting developing nations by providing access to quantum education and technology helps prevent a widening digital divide. Inclusive policies ensure that all countries have a voice in setting international quantum agendas. Capacity-building initiatives can assist countries in developing their own quantum research capabilities. The path forward requires a shared vision. We must recognize that the risks and rewards of quantum computing are collective. By embracing international collaboration, we can harness the full potential of quantum computing to address global challenges effectively and ethically. In conclusion, quantum computing offers incredible opportunities to advance our world, but it also presents significant challenges, particularly in privacy, education, and international cooperation. Safeguarding privacy in the quantum age demands robust legal frameworks, technological innovations, and ethical practices. Integrating quantum concepts into education prepares us for a future where these technologies are integral to our lives. International collaboration unlocks the potential of quantum computing to solve problems that no single nation can tackle alone. As we navigate this quantum future, it's crucial that we approach it responsibly and inclusively. By working together across disciplines, industries, and borders, we can ensure that quantum computing becomes a force for good, driving progress and improving lives around the globe. In conclusion, quantum computing represents a paradigm shift in technology and thought. It challenges our understanding of reality and offers tools to solve problems that have long been considered intractable. As we stand on the threshold of this new era, we must approach it with curiosity, caution, and a commitment to harnessing its potential for the betterment of all. The quantum revolution is not merely about faster or more powerful computers. It's about expanding human capability, exploring the depths of nature's laws, and opening doors to innovations that can enhance life on Earth. It's an invitation to reimagine what's possible and to strive toward a future where technology and humanity progress hand in hand. Thank you for joining us on this in-depth exploration of quantum computing. From its theoretical underpinnings to its practical applications and future implications, we've journeyed through a landscape that's as challenging as it is inspiring. The future is quantum, and together, we can shape it into a force for positive change.